Welcome back. So last lecture, we built a model of a polar solvent, which envisioned that we could grid up space, treat the complicated details of molecular structure in that polar solvent as just a system of dipoles. And we began to understand how such a model for a polar solvent responded to, say, the introduction of an ion into that solution. We're going to first today revisit that calculation again, work towards understanding how polar solvents solvate individual ions. That is still imagining that we can treat individual ions by themselves, so that we are working under sufficiently dilute conditions that ions don't interact. You might imagine that this is something you should be a little bit skeptical of, given the emphasis we've placed on how long-ranged interactions between charged species are. And so what we're going to then work towards is an understanding of how ions actually arrange themselves in space when they actually do interact. And what's exciting is that we can say something simple about such a complex process there too. Okay, so this lecture I like to think of as the physical chemistry of saltwater, physical chemistry of tears. What we're going to do is we're going to think back to our polar solvent. So we have some liquid here. You can envision water. And in that solvent, there are going to be some charges. And we know that there has to be an equal number of negative and positive charges, otherwise charge neutrality would be violated. We'd have a non-thermodynamic or non-extensive system. So this is a system we're considering, some polar solvent with some collection of ions. And the two questions very precisely we're going to ask is, how does a polar solvent accommodate a first isolated ion, and then second, how are ions arranged in space? These are so-called non-ideal effects. Effects due to being away from those dilute solution conditions that we can imagine that ions distribute themselves spatially independently. When we are talking about electrolyte solutions, then those long-range interactions make dilute solution approximations break down quickly. And yet, because of those long-range interactions, summing over lots of molecules in order to understand their response, it is still the case that we can say something fairly simple about this situation. Okay, so let's remind ourselves first of kind of the calculation we went through last lecture. So if we're going to imagine putting an isolated ion in a polar solvent, what happens? Well, there's a couple steps to think through this response. So the first thing that happens when I place an ion in a polarizable medium, like a polar solvent, is that the solvent polarizes and the way in which that solvent polarizes can be thought of as that solvent bringing up some effective opposing charge or counter charge to that solute. So the picture we can have in mind, say if we had a cation in solution, you know that its electric field lines, those lines of force that it would exert on a test charge, would be to push that test charge away. So we'd have radial field lines emanating away from a cation. That dipoles like to align in electric fields, means that those dipoles would align in those same radial directions, which means that if the dipole points from negative to positive at the non-pointed ends of those vectors, we're imagining that those dipoles have oriented such that the negative part of that dipole is up next to that cation. And so that's what we mean when we say that polarization is kind of like bringing up some opposing charge to the solute, in that you have this effect of shielding. Essentially, it's not that you neutralize that solute. The dipole is a neutral object. Even though it polarizes, it can't really neutralize an ion, a solute. Nevertheless, the local electrostatic environment in the vicinity of that cation looks a whole lot like there's this excess ring of countercharge that's been brought up to it. That intuition serves us well when we do explicit quantitative calculations, because a lot of the forms of the equations can be rationalized with this perspective. So that polarization of the solvent due to this ion can be drawn out like this. So let's put an arbitrary ion with charge Q in some solution. It generates a field. Let's call that field subscript ion, which we know is going to be proportional to the magnitude of that charge. Now that field generated by the ion then is going to induce a dipole in response of the solvent. So that solvent will align, generate a net dipole. Again, in the absence of a charge, there is no net dipole on average in the solvent. Water molecules can point in all directions equally likely. But in the presence of that ion, a dipole is generated. That dipole is going to have a magnitude which is proportional to the strength of the field that's generating it. In this case, the field due to the ion, which itself is proportional to the size of the charge on the ion. Now that dipole that is generated due to the charge itself generates an electric field that's going to act back on the ion. We call that field the reaction field. It's the reaction of the solvent due to its polarization. It is proportional to the size of the dipole. And the size of the dipole, as we just reminded ourselves, is going to be proportional to the magnitude of the charge. So the effective strength, or the effective interaction that the charge feels due to its being solvated in solution, is going to go like that charge squared. because the interaction energy of a charge and a dipole is can be written as minus the field the charge generates dotted into that dipole. The field that it generates goes like the magnitude of the charge, and the dipole that responds goes like the magnitude of the charge. So that interaction energy should scale like q squared. And should be favorable. Independent of the sign of the ion, there should be a favorable net interaction between that ion and the surrounding solvent. This is an interesting point itself. At this level of theory, there is no difference between cations and anions. Their action on the solvent is the same. And this is because we've neglected all of those sources of asymmetry in the charges. We've imagined that water is a dipole, and a dipole is this idealization where we have two equal and opposite charges separated over some distance. We know, of course, that water is slightly more complicated. Those charges are distributed around a water molecule in some slightly more complicated way, and you might expect then that the way water will solvate an anion or cation might be slightly different. What is exciting is that this approximation of treating water just as a dipole works incredibly well. Okay, so from this intuition that the interactions should scale like q squared, we can actually calculate explicitly the interaction energy between the ion and the induced polarization of the solvent. We'll call that subscript sol. This is the average interaction of the ion with the induced polarization. It's going to be proportional to, as we just said, minus q squared. And now we're going to integrate over all of the dipoles that were generated, which are distributed in space. The interaction energy goes like the field of the ion, which is from Coulomb given by his inverse square law, then dotted into the size of the dipole. And the size of the dipole also goes like the electric field due to the ion, another factor of q squared. This is going to be then proportional to minus q squared, an integral over just the magnitude of r times its Jacobian for r squared, having integrated out those angular parts of the spherical coordinates would give us some factor that we can include in that constant of proportionality. The field, then two combinations of such gives us 1 over r to the 4. And we're going to integrate that up to infinity, but down to the size of the ion. We're going to include only, we're going to imagine that the solvent exists only in some region past some excluded volume region that signifies the scale of the ion itself. So those are integrals we can do. And if we did them and accounted for those proportionality coefficients, that tells us exactly how big of a dipolar response we get from polarizing that solvent, accounting for things like the fact that the dipoles don't like to align parallel to one another, so that response is attenuated by some amount, we get that the average interaction between an ion and the induced polarization proportional to q squared divided by the size of the ion from that lower limit of integration, and the amount that it is attenuated due to interactions between dipoles as they align gives us this factor of 1 minus 1 over epsilon, where this epsilon, as we introduced last time, is known as the dielectric constant. That tells us just how strongly the solvent is going to respond to an electric field. And you can imagine that this dielectric constant is related to that microscopic polarizability we introduced when we introduced this kind of simplified model of a polar solvent. And we ended last lecture by a little bit of a discussion as to this dielectric constant, what its scale is. It's something which, if you see in this equation, has to be unitless, because the 1 in that parentheses is unitless. So if we noted different mediums that you could imagine solvating charges in, and what their corresponding dielectric constants are, well, by construction, if there is nothing to polarize, like I'm in the vacuum, that dielectric constant is 1. I'll take 1 minus 1. I will get no interaction. In fact, there's nothing to interact with. Does that make sense? A non-polar solvent something like an organic solvent, hexane, might have a dielectric constant of 2. Water, on the other hand, being a very polar solvent, has a dielectric constant of 80. It responds very strongly to electric fields. Now, an ideal conductor, something like a metal, which responds completely or fully to electric fields. Metals can polarize ideally in response to electric fields. It has a dielectric constant which is infinite. Now we'll note that 80 is awfully close to infinity. If I took 1 minus 1 over epsilon, where epsilon is 80, that is 79 over 80, which is awfully close to 1. Okay, so we've just carried out this calculation for what is the average interaction strength between an ion and the surrounding solvent. Now, thermodynamically, what we actually care about is not just that interaction, but rather what is the total change in the energy of the system as I take that ion and I put it in the solvent. Now, it turns out that those two calculations are very similar. Now, what we've neglected in the first part is the change in the solvent, but the particular form of those interactions, the fact that there's simple relationships between the response of the system due to the ion and how those dipoles would fluctuate generically, lets us find that the total change in the energy when an ion is added is just a factor of 1/2 as favorable as what we calculated previously. So that is to say that the total change in energy is minus q squared r ion, and that factor of 1/1 minus epsilon times a factor of 2. When we actually account for the rise in the energy due to those dipoles aligning parallel to each other, that's unfavorable. That raises the energy, which was lowered due to those favorable interactions between the ion and those dipoles. We still arrive at something simple, which is that the total change is just 1/2 the change that we had before. And if I'm being more specific, this is usually the formula which is known as the Born solvation model. You can think about that total change in energy. We've done this, reversibly. We've done a thermodynamic calculation where we've taken an ion from somewhere and moved it into the solvent. So this is equal to the reversible work to move an ion between something that doesn't interact with to a solvent which it does interact with. Well, one can imagine that a medium in which the ion would not interact with anything would be a vacuum. A vacuum is close to just is an idealization of what you might have in just the vapor. The vapor has dielectric, a typical vapor away from their critical points would have a dielectric constant which is essentially 1. So to a good approximation, this change in energy is a change in energy you would find if you moved an ion from the vapor to the liquid. That means that we take an ion at a fixed position in the vapor, we move it to a fixed position in the solution. We've moved one ion and computed a reversible work. This is at some constant pressure and temperature. So the relevant work is the Gibbs free energy. The change in the Gibbs free energy by changing one particle, well, that's what we mean by the chemical potential. So this is equal to the change in the chemical potential in going from liquid to vapor, but neglecting those translational states. So this is the change in the chemical potential at standard state. So indeed, in going through this calculation, what we have arrived at is an explicit formula for the change in standard state chemical potentials when I move an ion from the vapor, where it doesn't interact with anything, there's nothing to polarize, to the liquid. And so now we can really, from first principles, for example, by knowing dielectric constants of different mediums, say water and oil, we could predict without any empirical numbers what the partitioning, what the equilibrium constants would be for adding some dilute amount of salt to water and seeing how much is taken up by an oil phase, say, that it's in contact with. All right, but now to get to that kind of case where we have not just one ion, but many ions, the first thing I want to note is what this shielding of the dielectric response does to interactions between ions. So because the solvent polarizes, you can think of that generated polarization as shielding electric fields the electric field that an ion generated initially is stronger than it would be in the presence of a solvent, which orients its dipoles, neutralizing some of that electric field. And as a consequence, effective interactions between ions are weaker. So let's draw some pictures to understand that. So imagine I have a cation. It would generate an electric field that we drew at the beginning of lecture, radially emanating out. The solvent is going to polarize in response, bringing some amount of negative charge up. I'm drawing these all backwards. The solvent polarizes, bringing some amount of negative charge as they align with that electric field. And as a consequence, the effective strength of that electric field, the magnitude, is decreased. And that's true of an cation, or if we were to draw the same setup with an anion, electric fields point towards it as test charge is going to feel an attractive interaction, an attractive force, bringing it towards that ion. Again, those dipoles are going to align with that field, bringing some effective positive charge up next to the surface of that ion. If those two charges are in each other's vicinity, say they're separated by some distance, r, the potential that they'll feel is going to be less than the bare potential. It will still depend on the sizes of their charges, their separation distance, the magnitude of that distance, but will be decreased by a factor of epsilon. So epsilon essentially reports on how much charge is brought to the surface of an ion due to the solvent polarizing. And so from the perspective of the ion-ion interactions, the effective electric field that they feel after that shielding occurs is reduced by a factor of 1 over epsilon from that bare interaction. So ions interact more weakly in the presence of a polar solvent or a dielectric than they would in the vacuum. So that's a little bit of intuition that'll help us now ask or address our next question, which is how ions arrange themselves in space. And that is really a discussion of something called screening. Okay. So let's again draw our little solution that we're aiming to describe. There is some polar solvent that sets a dielectric constant, can polarize in the response of some ions. And now we have some collection of ions. That are away from those dilute solution conditions. Say it like that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, charge neutral. Very good. If I was to look, say, at some tagged cation and look radially out from it, what you should expect, because like charges repel and unlike charges attract, is that in the vicinity of a tagged cation, there should be an environment which is enriched in anions, or more generally, the environment of an arbitrary ion is enriched in its counter ion. That is to say that if I tag that positive charge, I looked out from it, I should see in the vicinity more negative charge than I see positive charge. And in fact, that's also true of the next cation, that I should have some buildup of negative charge. In fact, if I were to take in aggregate some region of the fluid, we know it has to be overall charge neutral. So that means that at large enough distance away from any arbitrary tagged ion, there is a distance over which I can move beyond, over which I see effectively a neutral patch of fluid. I don't notice that there was, say, a tagged cation at the origin. That's what we mean by screening. Screening is the accumulation of counter ions around a tagged ion. Oh, and there's a length scale associated with that screening, which determines the length over which I can move beyond that tagged charge and see an effectively neutral solution. So that's what we're going to try to work out, is how, what can we exactly say about that process of ion accumulation, counter ion accumulation, and effective neutralization of some tagged ion. Okay, so to do that, let's consider tagging an ion Q at the origin. A sharp question we can ask is, given that tagged ion at the origin, what is the distribution of other ions around it? So we have our charge here. It's in some solution. Give it another color for fun. It's going to accumulate some counter charges. Etc. If we looked out radially from that origin, we can define rho of R sub J given Q as the average density of ion type J, where J is a cation or anion, at position R, given Q at the origin. That's going to be essentially the quantity we want to try to compute. How do ions distribute themselves around this tagged ion at the origin? Noting that there are both cations and anions, so the way anions might surround the charge at Q might be different from cations around Q. Now, in some sense, we have the means already to answer that question by noting that the energy of an ion at R is just Qj times the potential at R. The potential, electrostatic potential, is a summary of the electrostatic environment due to all the other charges. If I wanted to know the energy of a specific charge at some specific place, I just need to query what that electrostatic potential is. Now, the difficulty is that that potential depends on the positions of all the ions. So if I want to know the energy of an ion at a specific position, and therefore use, say, the Boltzmann distribution to compute the probability that it would be at that position, well, I need to know the positions of all the other ions in order to compute that potential, which then makes this calculation difficult. We're going to simplify it using a so-called mean field approximation. This is something we saw already in the context of critical phenomena, where we could not ignore correlations between fluctuations in locally liquid and locally vapor-like cells. Yet those correlations make calculations cumbersome. So we simplified things by replacing a fluctuating quantity by its average. We're going to do the same here. We're going to replace a fluctuating electrostatic potential, fluctuating because the ions move around, by its average. And that average is going to be conditioned, dependent on a tagged ion Q being at the origin. Okay, so let's see how this plays out. So here, that's the setup. If we wanted to now ask the probability that a J ion, an ion of type J, is at some position R, well, that's going to be proportional to its Boltzmann factor, whose energy we reminded ourselves will be Q times the electrostatic potential, and that electrostatic potential we've replaced by its average. The constant of proportionality here is just 1 over V, because that electrostatic potential will decay at long distances. If we're in a macroscopic volume, that's a good approximation. If that's the probability of an ion being at some position R, we can compute the density of that type J ion by knowing just how many of those ions there are. So what we have here is that the density at some position R is just the bulk density times a Boltzmann factor that will tell us what positions ions are enriched or diluted due to favorable or unfavorable electrostatic potentials. And if we know that density, where the ions are, well, that determines what the electrostatic potential is. So you can see that the left and right-hand sides of these equations depend on each other. Specifically, the average electrostatic potential at R due to a charge at the origin. Well, there's a potential due to that charge at the origin, which is Q over R, and then a factor of that dielectric constant, the solvent that is polarized in the presence of the ion. That's the potential we would find if there was only one ion in the solution. In addition to that one ion, there are other ions that have distributed themselves at different positions. So I need to sum over all of those other positions. Positions are continuous, so that sum is an integral over all other positions over all types J. And then if there is an ion of type J at one of those positions, it's going to contribute its own field, which has the same form of that distance from point R, where we're asking for the electrostatic potential, times its charge and 1 over the dielectric constant. So if we unpack this, the potential at some point R has a piece from the tagged ion at the origin, and a piece due to all of the other ions. Each of which, through Coulomb's law, contributes a potential at that point R due to their distance from point R and their charge. That rho of J then just tells you the number of those ions at that point, or a proportionality constant to the probability that those ions are at that specific point. Now we have an explicit equation for rho of J up here. So we could put this another way. The potential at R due to a charge at Q has that direct piece, plus the contributions from all the other charges. The density at point R prime is given by that Boltzmann expression, which says that I take in the bulk density, and then the likelihood that a charge J is at position R just depends on that Boltzmann factor, which itself just depends on the potential that that ion fills at R prime. And in mean field theory, we, instead of averaging that exponential, we have an exponential of the average. We've replaced the fluctuating field by just its average value. This is something known as the Poisson-Boltzmann equation. Poisson, because this is a relationship between a field and a charge density. Boltzmann, because we use Boltzmann statistics to get that average charge density. And is really hard to solve because it's nonlinear. We have a potential both on the left-hand side and in the exponential of the right-hand side. In fact, people still, to this day, try to write computer programs to efficiently solve this equation. It's not an easy thing to do. But if ions are dilute, such that the average potential at any point is small. If that average potential is small, when I turn that into an energy relative to kBt, it too is small. That means that that exponential could be expanded, and the Taylor expansion of the exponential is 1 minus its argument. That turns this nonlinear equation into a linear equation, and in fact simplifies things even more if we note that this exponential lived under this sum here, and we look at the consequences of this sum. So if we sum over species J, the bulk density of that species times its charge, that exponential lived under that sum. Taylor expanding, I get a sum over types J, their bulk density weighted by their charge, minus beta as a constant comes outside. I have a sum over types J, that bulk density now times Q squared times that average potential. Now, if I sum over the charge times the density, that's the total charge density. Charge neutrality dictates that that term is 0. this term, the density weighted by its charge squared, we will define as something known as the ionic strength. It's essentially the simplest summary of how much charge we have, because if we just ask for the total amount of charge, charge neutrality dictates that that is 0. So if we put these together, we have an expression for the potential at R, again, due to the direct piece of the tagged ion at the origin, now minus twice beta, the ionic strength, over epsilon, an integral over R vector, that potential factors of 1 over that displacement. Now we have an expression which is at least linear in that potential on the left and on the right. You can imagine that that can be solved. Indeed it can. We'll quote that in just a second. Before we do, however, we'll note that ions have radial symmetry, so we're imagining that we'll be able to take this factor, integrate over its radial its angular coordinates, so we'll have a factor of 4 pi. This factor here must have units of length squared inverted, and is where all of the information about the solution is living. All the information about the other ions has now been rolled into that ionic strength. So let's actually define a length scale, call it lambda, which is including that factor of 4 pi, so we have a 8 pi beta I over epsilon. That whole quantity has units of length inverse, so if we then say that lambda is a length, this is a length known as the Debye screening length. Without even solving that expression above, we know that an important parameter will be that length scale. That's what naturally comes out of just dimensionless analysis, or dimension analysis. So if we actually then solve that equation using some tricks from Fourier transforms, we find that the average potential due to that charge at the origin has a factor of Q over epsilon R, what would be there due to just the original charge at the origin, but it is attenuated by an exponential with a characteristic length scale, which is that screening length. So if we plotted this function, at large R, that potential on average goes to 0. So for R much, much greater than this screening length, a charge that is at that distance doesn't feel the effect of the charge at the origin because those counter charges have effectively neutralized it. That length scale lambda then signifies the length over which the excess charge due to tagging a charge and insisting that it is existing at the origin, where we don't notice that that charge is there anymore. Okay, so we'll figure out more of the consequences of this screening and how we can actually use it to maybe say some things about our dilute solution theories before, and how we correct dilute solution theories, assuming that ions do place additional constraints on how they distribute themselves in space due to these interactions, and we'll work through that next time. All right, thank you all.